We are back, I think. Let's see. Yeah. And then I can color. I sure can. Okay, so let me put this back up here. We were talking about the Stork reaction. Which is a reaction between an aldehyde or ketone Thank you all for your patience. We used pyrrolidine. And we used an alpha beta unsaturated carbonyl. That's crammed, but you put it below the line, so you put it better off. Oop. Last one we're going to do is hydrolysis, H3O+. And the deal with the hydrolysis is, if you recall from looking at that last slide that I just talked about on the recording and didn't have a 5-minute break in here, is that you're going to have a nitrogen still attached up here. We need the nitrogen to go away. So this H3O+ is to hydrolyze off that enamine. What we will get from this is our ketone will be back after the hydrolysis step, and we will have added at that position our alpha beta unsaturated carbonyl. So 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. There would have been a double bond there, but it took a proton and then tautomerized, and turned into our carbonyl. I'm going to show you these steps, the mechanism for this. You can actually do the entire mechanism. And as a way of practicing, I recommend that you do every single one of these steps. Forming the enamine itself, you may recall, is a long process. Right? Making an enamine takes like 7, 8 mechanistic steps to get there. Right, so instead of doing all of the full mechanism, let me show you the steps. Step 1, we're going to form the enamine. Somebody tell me what that looks like when I react cyclo. I showed you this exact molecule, so never mind. Yes, you know what it looks like because you have it in your notes. That's where the cyclohexane, cyclohexanone, is going to turn into an enamine. The amine here is bound up in a ring. Just make sure you conserve that. Step 1, make an enamine. Step 2. Now that you have your enamine, that's the enolate derivative. That's the nucleophile. We're going to react the enamine the enone. We're going to react an enamine with an enone. Remember, I'm going to use, I'll write this out just because I'm now saying both of these words. Enone is a shorter way of saying an alpha beta unsaturated carbonyl. I actually prefer calling it an alpha beta unsaturated carbonyl myself, not because it makes me sound big and smart, but because it's very descriptive. There is a double bond next to a carbonyl between the alpha and beta position. So it's this big fat word that tells you exactly what's going on with the molecule. Enone's a little bit more cryptic, I think, of saying that. So we take our enamine, put this below in your notes where it makes sense. React it with our alpha beta unsaturated carbonyl. I won't show the whole mechanism, but the electrons are going to flow down. Look at the Christmas mechanism, you guys. The electrons are going to flow down from the nitrogen. Put these on the other side. Down from the nitrogen, over from the carbonyl. I'm sorry, over from the alpha carbon. And it'll be a conjugate addition. When you do that, the nitrogen with a positive charge there. And then initially, that's what you're going to have attached on the end, right? This O minus. That's going to take a proton and turn into a carbonyl. But I'll leave it that way for now as an enolate. You know that that takes a proton, turns into a ketone, so it gets back to this position over here. So the thing we need to deal with is I still have a nitrogen here. I don't want a nitrogen here. I want my carbonyl back. So how do I get rid of it? That's this last step, hydrolysis. So hopefully forming an enamine should be somewhat familiar. I hope that an enamine attacking a beta position of an alpha beta unsaturated carbonyl, while that sounds super complicated, is similar to what you've seen before. It's a nucleophile attacking this outside position. Hopefully we can see that as a nucleophile. Right. The last bit here, let's talk about the actual mechanism for hydrolysis, because I don't think we've discussed that part before. How do we get a nitrogen to come back off of the molecule? Questions about steps 1 and 2, though, before I carry on. Okay. Step 3, hydrolysis. Hydrolysis to lyse, to break apart with water, hydrolyse. Ultimately, what we're going to get, yeah, so really what's going to happen, I probably should have drawn this out. Let me show you this last final bit here, because that's where I'm going to start from. When you have the nitrogen with a double bond, 5-membered ring. Or with a negative charge. When you react this with H3O plus, the most stable way that this is going to float around in solution is, as I mentioned earlier, you're going to have your ketone version, not the enol. But then what's going on over here is this nitrogen has a positive charge, right? Electronegative atom, positive charge, not great. It's a lot better if we can get that nitrogen to exist as a neutral charge. This is an iminium ion. So what we saw previously is when you have an iminium ion and there are protons nearby, you can take those protons to make an enamine. So that's what's going to happen. The enamine is going to reform. So basically what's going to happen is water is going to give, or H3O plus is going to give a proton to this guy, neutralize it. Water is going to take one of these protons, the electrons get pushed onto here to make a carbon-carbon double bond. The carbon-nitrogen double bond pushes up, and so you get this enamine. This is what's going to sit in the flask, most stable. The reason I wanted to start from here is it's a little bit easier to show you the hydrolysis mechanism. Well, no, it's not, because I'm going to take you right back to where it was. This is the most realistic version of what's going to sit in the flask. The nitrogen with the positive charge is less stable. So yeah, I'll just keep going from here. Okay. Now that I've gone through that big long spiel, the first thing I'm going to do actually is put this back into the iminium ion. The way that's going to work is the nitrogen pushes down, electrons push over from that alpha position. sorry, the reason I'm stumbling over myself here is really the H3O plus is going to neutralize this ketone. This is going to turn back into the enamine, but then instantly goes back to the iminium ion. You might recall iminium ions because they are intimately linked to forming enamines. This goes back and forth. Okay, the iminium ion is a good electrophile. If you have water present, it can attack this carbon. This is the iminium ion is very similar to an activated carbonyl. So the oxygen here can attack that carbon and push the electrons onto the nitrogen. What do you think needs to happen next? Never seen this mechanism before. What? Yeah, this oxygen needs to lose a proton. Does anything need to gain a proton? Nitrogen. All right. So eventually what I'm trying to get to is I need a carbon-oxygen double bond, and I don't want to have a carbon-nitrogen bond here. If I break this bond as shown, it's going to leave me with a negatively charged nitrogen. Bad news bears. So I'm going to play a little trick here, as you've seen me do several times before, where I'm going to say plus minus a proton. Remember what that means is something in the molecule is going to lose a proton, the oxygen. Something in the molecule is going to gain a proton, the nitrogen. A base will take a proton here. This will take a proton from an acid. What I'm going to get from that is an OH, now neutral, a nitrogen that now has a proton and a positive charge. This guy's just hanging on for the ride. Now what? Well, the hydrolysis step actually occurred here. Water attacked this. That's where water got brought in for this. So the lysing part, yeah, I need to get rid of that nitrogen. So I would break this bond to get rid of the nitrogen. But if I break that bond, this carbon is going to have a positive charge. That's not great. So how do I deal with the positive charge that I would develop here? A base could take the hydrogen, or more likely what's going to happen is the electrons are going to just push down from that oxygen. It would. Right. So I get my pyrrolidine back. And then final step is a base. And let's show, since we're using H3O plus, the base that I'm going to use here is water. We'll take that proton. Get us back to our carbonyl compound. The hydrolysis step has a lot of mechanistic pieces to it, but keep in mind, so does the enamine part of this. So whenever we talk about a Stork reaction, if you were to draw the proper mechanism for every step of the Stork reaction on this whiteboard behind me, it would probably take up the entire whiteboard, right? The enamine mechanism itself would take up like to here, the beta addition probably to here, and then the hydrolysis process. So this is a massive set of reactions. You want to be a Jedi master at organic chemistry, draw that mechanism out. Am I going to ask you to draw that entire mechanism for points? No. What I would do is ask you pieces of it and say, here's some starting materials or intermediates for this reaction, run them and tell me about the next steps that occur from this. The mechanism is just too long. Questions about Stork? Or particularly the hydrolysis step. We were on a roll. I blame the computer malfunction, not the Stork reaction. I can tell you're all very jazzed about the Stork reaction. You're like, what is this cool thing? I know what I'm getting my family for Christmas now. It's an enamine. The reason that you want to get your family an enamine is that there's a couple really cool advantages to enamines. Speaking of really cool Christmas presents, this morning I impulse bought 2 Christmas ornaments that I am jazzed about. One is a Christmas ornament of Post Malone, like tattooed face and everything. It's fantastic, but he's got like a Santa hat on. And the other one is a Wordle square that has it's like Claus, Mary, something like that, like solves all the way down. And I think it's Santa is like the final thing for it. Anyway, super excited about my cheesy ornaments. My family's watching this. Hopefully it's after Christmas. The reason that they are going to love their Christmas ornaments and you're going to love enamines is that enamines are more stable than enolates. $4K. Why are enamines more stable than enolates? Go real simple. What's the, I know, same here. No judgments. No judgments. I promise you that. The tiredness. Enolate. What's the 8 in enolate tell you? Has a charge. Has a charge. Right? Enamines are neutral. Enolates are charged. Why is it nice to have a neutral species do this? Maybe your reaction is sensitive to basic conditions. Maybe your reaction cannot tolerate ethoxide in there. If that's the case, you go, okay, well, here, look, don't worry about the base. I'm going to go through this much milder reaction using an enamine, which is a much more gentle way of trying to get that carbonyl to react. And the second one that your family's not going to understand because they're new to this class. Oops. But is equally important is look at, well, no, it's not on here now. This thing, right? I started out with cyclohexanone. I just did a Michael reaction with cyclohexanone. You might notice that cyclohexanone only has 1 carbonyl. When I first showed you this reaction, I would have had to have had another carbonyl on there to make a beta dicarbonyl. You don't have to have beta dicarbonyls to run these types of reactions. Monoketones. Can be used in the Michael addition. Typically, it's a beta dicarbonyl. Well, that's lame. What if the molecule I want to work with isn't a beta dicarbonyl? Does it mean I can't run a Michael addition? No, try enamines. I was sponsored by Big Enamine for this lecture. I'm in Big Enamine's pocket. You guys want to see one? You're like, hell no, I don't want to see one. I want the bad man to stop. Let's try one anyway. Or heck no, sorry. Heck no, I don't want to try one. It's unrecording. It's harder to edit yourself. How we doing? Easy, medium, hard? Easy, easy, easy. Calm down. All right, acetone. What's easier than acetone? Nothing is easier than acetone. You see pyrrolidine show up in a reaction, I want your spidey sense to go off. That molecule is used a bunch for Stork reactions. If someone asks you, if a small child asks you, where do babies come from? You say pyrrolidines. Don't say that, they'll get really confused. Sorry, I had to put a ring in, Caroline. This is like the one, I need one thing. Make it like a little spicy. How do, what make? Any takers? Yeah. What you got, Hart? You speak, I'll draw your words. Cyclohexane. Ooh, maybe here, let me try and appropriately draw what you're saying. Okay, cyclohexane. Carbonyl, okay. On the what carbon? On the beta carbon, yep. So how many carbons should I attach to this beta carbon? 3. There's 1, 2, 3. And what else? Carbonyl, where? This one's harder. Where my cursor is. So now, or now. Look up here. This one, that one. Perfect. The alpha carbon turned into an enolate. Enolate, attack the beta position. Push that up there. Stork. I almost got to the Michael addition. I swear it's the last reaction. I'm going to get through this carbonyl chemistry. And then on Wednesday and Friday, we will talk about amine chemistry, and that'll be the end of it. Take today to reflect on your life and then put that into writing in your course evaluations. If you want to come talk about these reactions, today's a great day for that at Action Center at noon. Otherwise, I'll see you all on Wednesday. And before that, I will see some of you on Tuesday for the lab final, if you need a reminder that the lab final is Tuesday. The literature report questions in the lab final can be like, what's a review article? What does peer reviewed mean? I'm not going to ask you all individual things about your I'll find a way to. I will find it. That's right. Everyone gets their own exam. Your last quiz is on Wednesday. That's right.